Hi, in this video, we want to take a look at the discrete uniform distribution. All right, so what we've got for sampling space is we have a collection of items. And what we're going to do, we're going to put the same probability of each one being sampled as our probability. Since it's the same probability for every single item, we're going to go ahead and call that the uniform distribution for it. Now, this is the discrete uniform distribution, which is different from the continuous uniform distribution. The continuous uniform distribution will have like infinitely many possible values. It's along an interval. Here we are only concerned with a finite number of items, and we can list out all those items. All right, so discrete uniform random variable is where the probability that we get a particular value is equal to 1 divided by the number of possible values, so the number of items in our sample space. Now, the probability that we observe an item in a particular set is the number of items in the set divided by the number of possible values. All right, so this is by far the simplest probability we really could be working with besides like Bernoulli. All right, so let's look at an example. Let's say I go with Roy G. Biv as colors. So I want to have, let's say I have, this is my sample space, and I'm going to have a uniform, discrete uniform probability on this one. So I have 1, 2, 3, 4, 5, 6, 7 items. That means the probability of each item is 1 over 7. Okay. So the probability that X is equal to red is 1 over 7. And probability of orange is 1 over 7. Probability of yellow is 1 over 7, and so on. Now, the probability that we get red, green, or blue is going to be 3 over 7. Simplest probability we could be working with. All right, so now, if I'm in R and I want to start working with discrete uniform distribution, I'm going to use the sample function. All right, so what we do to be able to use a sample function, what I'm going to do, I'm going to pass a vector in as the sample space. So here, this X tells R what is the sample space. So in this situation, it's red, orange, yellow, green, blue, indigo, violet. It's my sample space. And then for size, I specify how large of a sample I want. Okay. And so for this example, the random sample was indigo, but it could have been any of them. Okay. So something about the sample function is that by default, it samples without replacement. Okay, so if I was to put size equal to 2, let's say, first one's indigo, the second one will be any other one than indigo. So it could have been red, orange, yellow, green, blue, or violet, but it would not have been indigo. All right, so there's a couple things that happen with this. So the sample space shrinks when I sample without replacement on subsequent sampling, but also the probabilities shift, because now I've got 6 items instead of 7. So now my probabilities go from 1 over 7 to 1 over 6. So the probability that I would have had red as the next observation would have been 1 over 6. Okay, so let's look at what happens if I just sample all 7. So I have 7 items, and I go through and I hit size 7 for sampling. And so here we see that on this example, we get green, red, yellow, orange, blue, indigo, violet. You'll notice that all 7 are present, okay? And none of them repeat. All right, so what it does is if I use sample and I tell it to take a sample equal to the sample space and size, so here V is a character string vector of 7, size 7, it's going to basically just rearrange the terms in a permutation. It's going to change the order. It's going to give me all of them. Okay, now what happens if I try to go with a number bigger than 7? So I'm sampling without replacement. So that means each color can only appear one time. What happens if I try to go for an 8th color? If I put size equal to 8, well, it's going to go through, it's going to sample the first 7, and then when it gets to 8, it's going to be like, whoa, 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 I can't grab anything. There's nothing left. And so what will happen in that case, if I leave everything on default, if I sample without replacement, if I try to take a sample size that's too big, I get an error. And so there's a problem. All right, so what we're going to do, we're going to sample with replacement. So sampling with replacement, what we're doing is I go up, I grab a color, I record it, I put it back in, I grab another color randomly, record what it is, I put it back in, and I keep doing this over and over and over. Okay, so previously, sampling without replacement is like I grab it and now I take it out and it's no longer in the upcoming sample space. I grab another one and I take it out, it's no longer in the sample space. With sampling with replacement, so without replacement, you notice that it's like it's not going back into the sample space. With replacement, I pull it out, I record it, I put it back into the sample space. I'm replacing it in there. Okay, so let's look at an example. So remember that I've got 7 different colors and size is 100. The only way I can have a sample size of 100 with 7 different colors if colors appear multiple times. So here I've got green, and let's see, here's another green. Here's another green. So we can see that all the colors are represented multiple times because of the sample size. Now, the sample function allows us to adjust the probabilities. So technically this will, if I adjust the probabilities, it will no longer be the discrete uniform distribution. But since we're talking about the sample function in R, this is a good time to talk about this. All right, so if I want different probabilities, I have 2 different ways to do that. First way is to basically do repetitions with items in the frequency. So if I leave sample as is, I don't mess with the probabilities. If I repeat a value, then that repetition is proportional to its probability. The other way I can go is I can actually manually say what the probabilities will be. So let's go ahead and let's look at the first example where we use vector frequency to get proportional probabilities. All right, so in this example, what I'm going to do, this is going to be my sample space. I have violet once, indigo twice, blue 3 times, green 4, yellow 5, orange 6, and red 7 times. All right, so what's going to happen is that proportionally, red is going to have 7 times the frequency of violet in my sampling probability. Orange will have 6 times the probability of violet. Yellow will have 5 times the probability of violet. Indigo will have double the probability of violet when I do my sampling. All right, so let's go ahead and do that. And so what I did to show that this will give us the results that we want, I went ahead and sampled 10 million items. Here's my sample space as defined up here with the repetitions on the colors. And I'm doing with replacement. And so now I go ahead and I take my sample. I get a table, so this counts the frequency of each color, and then I convert that table to a proportion with prop.table. And so now I can see red is 1/4 of the observations, orange is 21%, yellow is 18%, green 14%, blue is 11%, indigo is 7%, and violet is just under 4%. And if I go through and I start doing the multiplication, I can see that these are pretty close to the ratio that you would expect off of this. It's not exactly right, but if I increase the sample size, it would converge to those probabilities or those proportions. Now, the other way I can control the probability in the sample function is I actually set the probabilities to what I want them to be. So here I've got V. I'm just repeating what V was, how I defined it previously, Roy G. Biv. Now, what I'm doing is I say that I want red to be 7 times the probability of violet. I want orange to be 6 times the probability of violet, yeah, and so on. And so here I'm taking the numbers 7 to 1, and then I'm dividing by the sum of all the values. And so what that does, that this vector as a whole adds up to 1. All the values are greater than or equal to 0, therefore it's a probability vector. Now you'll notice that when I do this, I get values that are very close to up here. So we have 0.25, 0.25, 0.14, 0.14. All right, this one is a little bit different. Yellow is just a little bit different, but you see that it's pretty darn close. green is the same, blue is the same, up to rounding, up the same, indigo and violet. So things are really tight. And so here, this is like the theoretical probability. This is the observed probability from a different sampling. So now I'm going to do the same thing I did before. I'm sampling with the regular version, not the repeated version, regular version, 10 million times with replacement. But the kicker here is that the probability is different now. And so when I get the probabilities, I can see that once again, I get pretty close values here and here. See these yellow matches, green matches, blue's good. Oh, indigo, there's a little bit of a difference, but not much. And violet matches the theoretical values. All right, so this shows that we have different ways to go about this. So depending on my project, one may be better than the other for what I'm doing. So one reason that we would want to use this one with the vector frequencies is if I'm trying to resample my data. So let's say I'm doing something like Bootstrap or Jackknife. If I want to take my data, sample from my data, and use that as like a new, a new sample, then like in Bootstrap, then this technique will give me probabilities pretty close to what I see in my data. Now the Sampleint function is a specialized version of the sample function. It's actually under the hood, the one that's doing the work in R. What this does, this samples from the numbers 1 through n. So what we do, we specify the n, the largest integer value, and then samples 1 through n. Now under the hood, when we're using sample, this actually is what's being used because it's faster. And then what it does, it samples these 1 through n values, and then takes, if it gets a 3, it takes a third value from the sample space, sample function. But Sampleint, if I put down just a number, you'll see that it gives me all the numbers 1 through 10, just random permutation. If I say n is equal to 10 and size equals 30 with replace equals true, remember if size is bigger than the sample space, it has to be with replacement, and it gives me some sampling. Now what happens if I give it a non-integer? So let's say that I say n is equal to pi. What it does, it takes the largest integer less than or equal to the number that I specify, and then proceeds as usual. All right, so now let's actually look at a little bit of mathematics about this for discrete uniform distribution over a range of integers. All right, so here I'm going to talk about, I've got some numbers and their integer values. I have a minimum value, I have a maximum value, and all the ones in between, I'm going to go ahead and I'm going to have uniform probability on them. So lowercase n is the minimum possible value. Uppercase n is the maximum possible value. My sample space is little n through big N. So if little n was 10 and big N was 20, then my sample space would be 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Okay, so how many items do I have in here? Well, I have capital N minus lowercase n plus 1. So notice that it's plus 1. Because if I started at n plus 1, this would be capital N minus n, but I don't have that. So it's capital N minus lowercase n plus 1. What's my expected value? Well, my expected value is the mid-range of the sample space. Very nice, that's very easy. And then my variance is the difference between the maximum and the minimum, and then the difference plus 2, and that multiply and divide by 12. Boom. All right, so how do we get the expected value? To get the expected value off of this, I need this special summation formula that goes 1 through m. So if I take up the numbers 1, 2, 3, 4, 5, 6, add them all up, it's going to be 6 times 6 plus 1 divided by 2. So it's a nice, quick, easy formula. The largest number plus 1, multiply, divide by 2. That will be the sum of 1 through that value. Okay, so let's go ahead and let's figure out our expected value. So remember, expected values are the value times the probability, and then add them all up. Okay, well, here, this is a constant number with respect to the summation. So I'm going to go ahead and factor that out. So here, this fraction gets factored out. All right, so now I have the numbers lowercase n through uppercase n. So I want to use this formula up here that we talked about, but I can't because I need it to start at 1. Notice that I is equal to 1. My lowest number in my summation must be a 1. So what I'm going to do, I'm going to add on 1, 2, 3, 4 up to n minus 1, and then I'm going to subtract off exactly those same numbers. So I'm taking the numbers 1, 2, 3, 4, 5, 6, all the way up to n minus 1. I'm adding them into this summation, and then I subtract them off. If I add it and subtract it, that's the same as adding 0. I have not changed the sum. All right, so now in this format, I can use this formula here. So you'll notice I have capital N and lowercase n. I go in, so this one is capital N plus 1. Now I have lowercase n minus 1 in this position, and then I have a plus 1 gives me this one. And then I subtract. All right, let's mess with the fraction that gives us this. Okay, and so now I look at this and I say, well, I would like to simplify this. I notice that this is almost divisible by that, not quite. This is almost divisible by that, not quite. What I need to do, if you notice this, if I subtract off little n times big N, that's going to be divisible by this after I factor. And if I add on little n big N, this part is going to be divisible by the base of by the denominator of this fraction. So then we go ahead and factor. Then I cancel, and boom, I get my expected value. Easy peasy lemon squeezy. And so the expected value here is exactly what we would want it to be, what we intuitively would think it is. Now for variance, I'm going to do something very similar, but this time I'm going to take the sum of squared items. So 1 squared plus 2 squared plus 3 squared all the way up to m squared is equal to this formula here. Okay, so now the next thing I'm going to do is I'm going to do a little bit of statistics hocus pocus. I'm going to remember that if I have a data and I shift the entire data left or right on the number line, and I keep everything relatively distance between data points the same, I don't change my variance. The spread doesn't change. So I'm not going to work with the x that I have defined above. I'm going to work with a similar one. I'm going to take all of the possible values in the sample space and subtract lowercase n. Why do I do this? Because this will make this summation easier in a moment. Okay, so I know that the expected value of y is big N minus little n plus 0 divided by 2, because that's the mid-range of this one. Okay, I could simplify this with plus 0. Now the variance of x is equal to the variance of y because of that translation in variance of aspect. And so I'm going to use the variance formula of expected value of y squared minus expected value of y squared. All right, this part I know because I have it right here. This part I don't know. Okay, so let's go ahead and compute this. The expected value of y squared is, by definition, now I'm working with y, it's going to be the sum of the y squareds divided by their probabilities. Well, I recognize that this fraction is a constant across the summations. I factor it out. Boom. Okay, so now I see this. I know that I'm going from 0 to n minus 1. Now, when the 0 term isn't going to change anything in the summation, so I can go ahead and invoke this, because adding 0 doesn't change anything. 0 squared doesn't matter for this. And so I use this formula with capital N, lowercase n for each of the m's. And I get this wonderful fraction. Now I'm going to sit down, I'm going to do a little bit of math, and I'm going to simplify that fraction. Okay, so now at this point, I know the expected value of y squared, and I know the expected value of y. I can use this formula to compute the variance. All right, so here, variance of x is equal to the variance of y, using my formula. Now I just start plugging and chugging. Here we've got some squaring going on, simplify that. And then I notice I have n minus n with even numbers on the bottom both times. So I go ahead and do some factoring to make it a little bit simpler. So I get this fraction pulled out. That way I've got less gunk for my fractions. And then now I just go through and do the whole common denominator thing of 6 and simplify this into, so this becomes just one fraction. Do some subtraction, I get this, and boom, we get the result that we talked about earlier. All right, well, that's all I've got for you. Take care and goodbye.